we are taking a detour into chapter 9. Now, you will see why we're taking this detour probably by the end of class. You'll see why I think what we're about to cover, fits so well with what we just covered. And that's why we're doing it. What we're going to be doing, we're going to be looking at the geometry of parabolas. And in particular, well, that's in particular, but in general, we're going to be thinking about how to manipulate graphs of functions. And you'll see exactly what I mean by that in just a few minutes. So the idea is we're going to start by working with just parabolas, but everything we discuss is going to be true for any given function. And so, but parabolas are really good to start with when you're doing this because they have certain, they have some interesting properties. We will talk a little bit about that. Well, we'll get into that. So I want to give you a broad overview here. So let me I had a few points I wanted to say. So we're going to go over the geometry of parabolas and manipulation of graphs of functions. And then we're going to return to some chapter 8 stuff, in particular applications, which you know what I mean, word problems. And so I'm sorry, but we'll get there. They are super important. I hate to say that. It hurts me as a guy who did pure math to say no, like the applications are important, but they really are. And so we're going to do some. I'm sorry. I'm going to go ahead and apologize now. So, okay. So for the next few days, it will roughly coincide with chapter 9, sections 2, 3, 4, and 5. And it's not going to be necessarily in that order. We may or may not cover all the stuff that's in those, but if you're having trouble with any of the concepts that we are going to go over this next week, maybe more, you could use chapter 9, sections 2 through 5 as supplementary material. It's what I find is always nice is to have a different perspective. And in fact, what's sometimes really nice, if you have a teacher who's teaching out of a specific book and you run into some problems, this isn't just for math, right? This is like, I did this in particular, I did it a lot in chemistry. I would go to the library and check out a different textbook and see how that author presents the material. And sometimes it's nice to just have some contrasting material, to have the same thing from 2 different points of view. Sometimes that could open up your mind. So the stuff from chapter 9, sections 2 through 5 is what we're going to be covering. And like I said, I'm not going off of that stuff. And so you could get a nice fresh perspective from looking at that stuff if you need it. If you don't, cool, great, then I'm doing my job. Otherwise, yeah. So any questions before we jump into stuff today?
No.
Okay. Let's do a little review of functions. So I'll write down a function. Now I'm going to start with something really ugly and really scary. So, but I'm just doing this to illustrate a principle. So here's this. F of x is equal to 1 over the square root of x squared, let's go plus 1. Okay, really ugly thing. We're not really interested in this thing per se. I want to start with this example to just show, like, it doesn't matter how complicated your thing is. What we're going to be talking about today will apply no matter how complicated it is. So now, remember, functions are an input-output relationship, right? This x means that that's the variable, that's the thing that you're going to put into the function. And this whole symbol basically means that the output is what you get, and I kind of imagine little parentheses around here, like that's your output right there. The number that you get when you plug in, say, well, let's do one. Let's go f of 1. plug in f of 1. Now, 1 is my input. And so I'm going to go, okay, 1 over, what do I write down here? The square root of what?
1 squared plus 1.
1 squared plus 1. And what did your brain do? Well, let me tell you what your brain did. You said, well, hold up, wherever I see an x, I just replace that x with 1 because that's what it means, right? I plug that number in. And one thing I'm going to say is really going to help us out today, especially, is to think about this as in parentheses, right? Like whatever we put in there goes into that and gets squared. And so if we wanted to, so when the input is 1, the output is, and I could do some simplification. I could just say, well, 1 plus 1 is just 2. And I know that the square root of 2 doesn't reduce any further, so we're perfectly fine right there. We could say when the input is 1, then the output is, well, that entire thing right there, again in parentheses, thinking about it that way, then f of 1, and this also is the output, right? Okay. Now, what happens if I did f of x minus 1? What do I need to write? You tell me what to write. I'll start you off by doing this picture right here. Now, what do I write right there?
X minus 1 squared plus 1.
Now, do you mean x minus 1 squared like that?
No, parentheses.
No,
Yes.
in parentheses, right? We take whatever that is and square it, right? We could even imagine that the original thing does indeed have those parentheses, right? It's just, we really don't want to mess this up. And I'm, okay. And so we do that, okay? That's what that would be. All right. One last question. If I did this, f of x minus 1. It's a little bit different. I'm not plugging in x minus 1 into here. I'm just plugging in a regular old x, and then I'm taking this, and you can imagine this because, well, this represents your output right here. That f of x represents the thing you get when that happens. So we could say, well, that thing right there, f of x, is that output. The output is 1 over the square root of x squared plus 1. And then once you have that output, then you subtract off 1. And so that would be that guy right there. Everything, you good with all of that stuff?
Yeah.
Okay, right. So I just reviewing, we're going to do a little bit more review, but I'm going to actually have you do some questions here. I'm going to write a few things on the board. You take a few minutes, work them out, and then tell me what you get. So given, so here we go. Given f of x equals x squared plus 1. I want you to compute or write down a formula for each of the following. Write down what is f of x minus 1, f of x minus 1, f of 2x, finally, 2 f of x. Okay, so I'll give you a minute. Let me know when you have all of those written down. You good?
No.
Oh, sorry.
I'm sorry. I'm having a really hard time thinking.
Okay, so let's just go over them then. That's cool. So so remember now, what I'm going to be thinking about each time here is if I'm putting something into here, what that means, just by what this says, is I take whatever that thing is, square it, and then I add 1. And so in the first case, where it says x minus 1, I'm just plugging in x minus 1. And if we wanted to, yes, we could go through and multiply all that stuff out. But really, that's all that means, right? And you can see that, right? Like if that were a smiley face, I would just replace a smiley face there. Since it's a x minus 1, I just replace that with an x minus 1. So let's skip ahead and do, by analogy, the same thing here. What would that guy be?
2x squared plus 1?
Yeah, and we're going to think in parentheses here because we don't want to shoot ourselves in the foot, right? You don't want to say, oh, it's 2x squared plus 1, so you go 2x squared plus 1. That ain't going to work, right? That's not the same thing as that. Like this says you take 2x, that's what you throw into the function, and so that entire thing gets squared. And so yes, 2x squared plus 1. Okay, now in this case, where this is saying take the output of f of x. And so, right, f of x, I could just actually replace that right there. If we think about this, this is the thing I'm trying to get my head around. And I could say, well, hold up, that equals that right there. So in the same way that I use parentheses here to kind of keep myself honest, I could do the same thing here and say, well, this, in fact, I could think about this thing means the output that I get right there. And that, I'm just going to use this right here. It says that this is equal to that. Anytime you have something is equal to something else, you could replace the symbols. And so I'm just going to replace the symbol. And in this case, I get, okay, I'm going to replace the symbol. So I'm going to use my parentheses. I'm going to say, okay, x squared plus 1 is the thing. Just like that. Technically, I'm done, but I mean, we could simplify this. It would be easy to just drop the parentheses and say, okay, that's x squared plus 1 minus 1, which we could write as just x squared. So completely simplified, that would just be x squared. But it's exactly equal to this. And this is kind of nice because you could see it. Oh yeah, that's f of x right there. And that's, you take the output. So the output is what you get. Then you subtract 1. Subtract 1. Yep, that's what that is. And there I just simplified and made it look a little nicer. Okay, so by analogy then, we have here, we're saying 2 times f of x. So let's wrap our heads around that. Same way we could say, well, hold up, I have f of x equals something. So I'm going to use parentheses to my benefit. I'm going to say, well, this is the output we get right there. And so, right, that's some number after you do some calculation, right? You plug in a 2, you get a 2 squared is 4 plus 1 is 5. It's some number. And it says to take that number and multiply it by 2. So just, I know that f of x is kind of spread out and there's pluses in there. And so I'm going to put it, think about it in parentheses and say, okay, in that case, now I could just replace the f of x with this bad boy right here. So in other words, what this says is You put some number into F, you get some output out of it, and then you multiply it by 2. And if I wanted to, I could simplify this a little bit, make it look a little nicer. Either way, right? All we're doing is taking 2 times the output there. And again, we can write this either way, but I'm going to go ahead and write it like that. Now here's something to notice. This is the type of manipulation that we're going to be working on over the next week or so, is what happens when I add and subtract from inputs and outputs. When I add a number to the input, what happens to the graph of the function? When I add or subtract a number to the output, what happens to the graph of the function? That's what we're going to be working on today. The next thing we're going to be working on is what happens when I multiply the input by something, multiply or divide by something, and what happens when I multiply or divide the output by something. And we could see, I wanted to use these right here just to show this, is that these are not the same thing, right? Subtracting 1 from the input gives us this, and in fact, I'm just going to go ahead and do this. I'm going to square this out. That gives me x squared minus 2x plus 1, then plus 1. So you see what I did there, right? I just squared out that guy right there, and now I add 1 to it. Right? Is that clear what I did? Kayla? Are you there?
Yes.
Okay. So is that clear what I did? I just manipulated that?
Yes.
Okay. So then that is x squared minus 2x plus 2. And we can see that that is not the same thing as x squared. Right? So the point is, subtracting from the input is not the same necessarily as subtracting from the output. So f of x minus 1, doing that in the inside first, is not the same as doing the function and then subtracting 1. Okay. Ditto right here. These guys are not necessarily going to be the same either, because check this out. When we multiply the input by 2 first, we throw 2 times the input. In this case, we end up getting, well, 2x quantity squared is the same as 4x squared plus 1. I just rewrote that in the same way that I did earlier, right? And I can see that that is certainly not the same thing as this, right? 4x squared plus 1 is not the same thing as 2x squared plus 2. That ain't going to happen. Well, at least not for every single value. There's going to be like 1 value or 2 values where it works. But in general, doing this is not, so multiplying the input by 2 is not the same thing, does not give you an exactly equal thing as multiplying the output by 2. All right. Is this making some sense?
Yeah.
Okay, so now that we have that, we're actually going to start talking about geometry.
Oh boy.
Well, the geometry of parabolas.
Oh.
Yeah, we're not doing Euclidean proofs and stuff like that. We're just going
Oh gee, no, please.
we're going to start. Say what?
I spent a whole year doing that last year. No, thank you. No more.
Yeah, no, and you probably won't go back to anything like that. When I say geometry, I'm talking mostly about graphs and stuff. So,
Okay.
So let's take a look at x squared. So x squared looks like this. It's a cup. It's symmetric about what we say about the y-axis. That is, if you took a mirror and placed it right here on the y-axis, this is a mirror image of that. I'm going to call this f of x. That is, the output values are equal to x squared. This is a rule which tells me how to get output values for any given input value. When my input is 0, what is my output?
0.
Yes. Plug in a 0, you square it, you get out a 0. Okay. Now, what happens when I plug in a 1? What do I get?
A 1.
Why? Because 1 squared, right? F of 1 says to take 1 and square it, and you get out a 1. And so, okay, there's a 1 right there. What happens when I plug in a negative 1?
You get a 1.
You get a positive 1 because a negative squared is a positive, and that's why this thing is indeed symmetric, right? I don't care how far over this way you go. You go to 27, you plug it in, you get out 27 squared. If you went to negative 27, you square it, you're going to get positive 27 squared. They're going to be the same thing, right? We'll do a couple more. We want to do a couple more points here. What happens when I plug in a 2? What do I get out?
4.
Yep. What happens when I plug in a negative 2?
4.
You sure it's not negative 4?
Yeah.
Yeah, okay, good, good. All right, so that is why a parabola looks the way it does. The reason I want to use a parabola, like your book, when it first introduces this topic that I'm about to introduce, which is going to be what I call shifting and lifting functions, but it's the translation of functions. We're going to be sliding them to the left and sliding them to the right. We're going to be sliding them up and sliding them down. Your book starts with absolute values and lines. Problem is, a line, at least this is the problem I have. A line doesn't have a distinct point on it. Like, here's a line. Here's a general line. The thing is, if you look at this part of the line right there, it looks exactly the same as this part of the line right there. A line doesn't have distinguishing features, right? It pretty much looks exactly the same. In fact, it looks exactly the same everywhere you are along the line. And so it's kind of hard to trace or to really get a grip on what happens when you shift it up, say. Like, let's say I shifted this line up by 1 unit. So let's say we were right here at 1. My output is 1 right there. And I shifted the entire line up here to 2. And I have this new line. It's now parallel. Now, when I'm looking at that, it's like, well, wait a minute. Did I really shift this up? Or did I actually just take this line and shift it to the left? It's kind of ambiguous because, well, it's a line. It looks the same way everywhere. And indeed, shifting it up by 2 is the same thing as shifting it to the left by 2 because it's a line. Parabola, though, parabola has a distinguished point. We call that point the vertex. Have you heard that before?
Yeah.
The vertex of a parabola, right? Like over here, this parabola kind of looks like a line, and it kind of looks very similar to this bit over there. They're just in kind of in opposite directions, but this point is distinct, right? What I like to do, and I'm going to move parabolas around, I like to think about, well, what happens when I move that one point right there? And that's how we're going to do this. We're going to say, well, every parabola generally looks like a cup, and it has in this case, a minimum, or it has a vertex. In this case, it's a minimum, but if the parabola looked like this, it would be a maximum. But we're just going to call that the vertex for right now. And it will be really nice to be able to say, well, how does the vertex move with all of this? Okay, so that's just want to go over that. Okay, now we're going to graph a new function now. We're going to call it g of x. Can you see that? These are brand new markers, man.
I can barely see that.
Man, I really wanted to use different colors. Let's see. Does this work? How about that? Can you see that guy? Is that better?
Yeah.
Red better? Okay.
Yeah.
We'll do red. Brand new markers. Really looking forward to this. But anyway, okay. So g of x. We're going to do this. X minus 1 quantity squared. Now, these things are related. And if you're thinking about that first exercise we wound up with, I'll bet you could come up with how they're related. But we're not going to think about that right now. We are just going to go through and draw this guy out. So let's do the same thing I did before. When I plug in a 0 into G, what do I get out?
Let's see.
Okay.
1.
Yeah, because and here I'm not going to use my brain. I'm going to say, okay, symbols here. That needs to match that. So that's that. Okay, so 0 minus 1 is indeed minus 1. I take that and square it, and I get out a positive 1. Okay, then. So G, this red function that I'm going to draw, when I plug in a 0, I get out a 1. So, boom, he's right there. All right, let's go on. Let's do the same order that we did before. When I plug in a 1, what do I get?
Zero.
Yeah, that's 1 minus 1, right? We plug it in without using our brains and say, okay, when 1 goes in, then 1 gets subtracted by 1, and I get a 0. 0 squared is 0. Okay, so when I'm here at 1, I'm down at 0. I think the next thing we did actually was negative 1, but let's just finish going this way. Now let's go, what happens when I plug in a 2? What's G of 2?
One.
So
Yeah, 1.
2 minus 1, yep, 2 minus 1 is 1. Squared is 1. Okay. Let's do one that we didn't do last time. Let's do 3. Let's say I plug in a 3. What is G of 3?
Well, sorry. 4.
It's what? I'm sorry, I didn't hear you.
4.
Yeah, it is. Because 3 minus 1 is 2. You square that and you get 4. In fact, it's starting to look like we just took all of these points right here and shifted them to the right by 1 unit. Huh. I want to do a couple more here because I want to make sure something squirrely isn't going to happen when I start using negative numbers. I really want to make sure that this picture that's starting to evolve, it's starting to look like I'm just taking each one of these points here and shifting them over by 1 unit to the right. It really looks that way. Let's just make sure that this is going to continue on. What happens when I plug in a G of negative 1? G of negative 1 is what?
One. 2, 4.
I believe so, because I plug in a negative 1. I get minus 1 is minus 2. Minus 2 quantity squared is +4. So when I'm over here at -1, I'm up here at +4, just like that. We could keep going and keep going, but I'm feeling pretty good that all this thing has done by subtracting 1 from the input. It looks like all I've done is I've taken each one of these points and shifted them to the right by 1 unit. Looks like that's what we've done. And indeed, yeah, I mean, if I could draw, it would look much better. But you can imagine that this is all we've done. You know, why is this? This is one of the things that really, like, it seems backwards, doesn't it? We subtracted, and it moved to the right. That seems really backwards to me. I don't know about you, but I would think, wait, you subtracted. In other words, you brought in a negative number and it pushed you to the positive numbers. So what I'm about to do right now, this is just to conceptually wrap our heads around it. If this doesn't jive with you, don't worry about it. Like, this is not something you're going to need to know. This is one of the few cases that I'm ever going to say you could just memorize the fact that if you subtract off a negative number, that if you subtract off a positive number from an input, then you shift the graph to the right. But I do want to go into why this is the case. If you think about this, imagine that you are running along this slope, or our original function. Here's you're running downhill. Maybe I'll give you some hair. Sorry, now you have hair. Okay, so you are running down here. It used to be the case that when time was 0, you were at 0, right? In other words, when your input was 0, you were at the height 0. So if you're thinking about how high above the ground you are as you're running and you're looking at your clock and the clock says 0, you happen to be stepping at 0 elevation. And then as time went on, right, after 1 second went by, you were here at 1. Sorry, I made you bald again. Okay, there we go. So there you were. After 1 second went by, you were at 1. This says set the clock back. You're basically setting your clock back. So it takes you a longer time. It takes you an additional second to get down to 0. So since you've set your clock back, you don't get to 0 until an additional 1 second has gone by. This bends my brain. It should probably bend your brain too. But part of this is for the moment, we're just gonna believe that this is true. And this is the explanation why. Because subtracting from an input is like setting your clock back. That's one way of thinking about it. And then you could also say, well, then when will I come back up? When will I be back up here? Well, if I set my clock back, it's going to take an additional second to get back up to this point. Originally, it took me 1 second to go from here to here. It still takes me 1 second. My clock has been set back, so I'm not going to get there until later. I'm not going to get there until my clock hits 2. So that's what's going on there. Okay. You confused yet?
Yes.
Yeah, it's pretty confusing. And this whole thing about the clocks and the running and stuff like that, honestly, like I never think about it. I have it in my head. What we're going to get to today, I have this picture in my head about what happens to graphs when you subtract from the input and add to the input. I know that when I subtract from an input, it moves it to the right. When I add to an input, we're going to see it moves it to the left. I believe it because I've done this very thing before where I plug in the numbers and go, yeah, I subtracted off 1 from the input value and it moved this guy to the right. So, okay, I buy that. This whole thing, but then if you ask me to justify it, I got to go into this whole thing about time and clocks and different frames of reference. And it seems a little tacked on, and honestly it is, but I believe it. And so I think it's okay if you believe that this is true. Like we went through and we did this and we saw like, yeah, it ends up moving to the right. If you believe that, then you could just remember that subtracting from an input value shifts your graph to the right. Adding an input value is going to do the opposite, as we're going to see right now. So give me a second to kind of clean this up. Any questions before we go on?
No.
Okay. So we subtracted from the input. That's all we did. And in fact, let's just double check that. This function, this g of x right here, I got that. Isn't that exactly the same thing as f of x minus 1? Is that any different from if I just said, here's f of x, here's f of x minus 1? That's what you would put, and you'd say, yeah, that's the same thing as that. There's no difference there. We're giving it a new name, g, yeah. But the idea is I've taken the input and subtracted off a positive number, and it shifted this guy to the right. Okay. Let's do a new function. What happens when I add a positive number to the input? So let's plug in a bunch of values. When I plug in, boy, I'd really like to use green, make this look a lot better. I'm going to do green. I hope you can see. I'll press really hard. Shake this thing out. Oh yeah, nice. G of x. Is that visible? That's better. G of x equals x plus 1 squared. We could even call it h, but whatever. Why did we get rid of that? Okay. Anyway. Whoa! Wow! Look at that. That's really leaking.
Oh dear.
All right.
That's not good.
Glad it wasn't red. I would have freaked out. All right, now, so let's do. Now I just said this shifts it to the right by 1 unit, but let's just make sure of that. Let's start with 0. Plug in a 0. What do we get as an output?
Plus 1 squared, right? Okay, so g of 0 plus 1 is 1.
It is 1. G of 0 is 1 because we get 0 plus 1 is 1. Squared is 1. And so when we're at 0, we're here again at 1. Okay, let's go left this time. What is g of negative 1?
Zero.
Minus 1 plus 1 is 0. Squared is still 0. And so well, this is where the payoff is really. Is like I said that there was one point on a parabola that was distinct. The point that I like to stop and think about. That's the vertex. That's either the lowest or the highest point, depending on what the orientation is. In this case, it's the lowest point. And we can kind of see what's going to happen here. Is like, it's as though I took my 0 and shifted it to the left by 1 unit. And it's like, well, hold up. You know that you're taking something and squaring it, right? Like that's what we're doing. We're taking some value and squaring it. What's the lowest value that it could possibly take?
Like
Yeah, I mean, it's so long as we're not using complex numbers, which we're not. We're only going to put in real numbers. That's kind of what this means by having an input axis like this. This means like we're only taking the real numbers. And so, okay. Sorry, this thing is just bleeding all over me. Man. So, all right. So, since that's like the point, right? That 0 point, it's the lowest point it could ever get. What I could do is just say, well, for what value will I get a 0? The only way from this guy that I could get out a 0, the lowest value, is if the input is 0. And we saw that the only way of making that guy 0 is when x is -1. Plug in a -1. -1 plus 1 comes out to 0. That's what you square and get 0. Take any other number that's not -1, and you're going to get something that's not 0. It might be -5, and you square it and you get +25. It might be +3, then you square it and you get +9. But the thing is, the only way to get that lowest point right there is when that value right there is 0. And then I know what the shape of this thing looks like. If I know that that's where the vertex moved, I could say, well, if the vertex moved there, well, I know what this thing looks like. It's just a cup. You've taken this and shifted it to the left by that. And this makes me feel good because, yeah, it should, after moving 1 unit over, it should go 1 up. Because that's what the original one did, right? The blue function, f of x. When I was here at 0, 0, right, at its vertex, I moved over 1 and it went up 1. And that's what we're seeing here. This guy got shifted over 1 unit here to -1. I move over 1 and it went up 1 because it's a parabola. That's what it does. Okay, let's check and see if this trend continues, because the original one, right, started at 0 and it was at 0. We're at the vertex. We went over 1, it went up 1. We went over 1 more to 2, it went up to 4. So now my next step over by 1 unit should go up to 4. Let's see what happens when I plug in a 1 into G. What is G of 1?
Four.
It is 4 because I plug in the 1. I get 1 plus 1 is 2. 2 squared is 4. And indeed, yes, I've moved up now to 4. And if we were so inclined, we could go and do -2. -2 plus 1 would be -1 squared is 1. Okay, yep, it comes back up. If we wanted, we could go to -3. -3 plus 1 is -2 squared is +4, and so on and so forth. But the cool thing about parabolas is it has a distinguishing feature. And I could see that, well, I know what this guy looks like. I have seen x squared 1,000 times. I know that it starts here and goes up like that. It has its vertex at 0, 0. Therefore, if I've shifted something by some amount, let's say I have some function that looks like this. I know I keep using G, I'm sorry, but here, give me a second. If I shift it by some amount, let's say -5, what I could do is say, well, hold up, what happens to the vertex? Well, the vertex, that lowest point happens when the output is 0. The only way to get an output of 0 is if that thing is 0. So what value of x gives me a 0 right there?
Hold on, sorry.
Okay.
Five.
5. If I plug in a +5, you hear what I'm saying? If I plug in a +5, then 5 minus 5 is 0. And oh, we have just shifted that point over here to positive 5. And nothing else has changed. Plug in a 6. What happens? 6 minus 5 is 1. You go up by 1. I'll kind of extend this a little bit. This is 5. This is 6. This is 4 right here. And now it's the same thing because we're not doing anything else. All we're doing is taking an input and squaring it, right? Plug in a 5, you get the 0, so you end up right here. Go over by 1, and you have 6 minus 5 is 1 squared is 1. Go over to 7. 7 as an input. Well, you're just basically dragging the clock back by 5 units and saying, yeah, okay, 7 minus 5 is 2. 2 squared is 4, and so on and so forth. Going back by 1, you'll have 4 minus 5 squared is negative 1 squared is 1. Go figure, it's going to have this same look. Go back 2 more. It's the same as having your original and going back 2. You're at 5, you go back 2. That's 3 minus 5 is negative 2. Squared is 4, and so he comes up here, and that's what happens. The thing is, I'm not too concerned with all of these points. I could pretty much just say, well, what happens to the vertex? If I know that the vertex has been shifted over 5 units, because that's what that means, right? And you even found it. I didn't tell you where the vertex was. I asked, what input will give you 0 as an output? And you told me, well, if x is equal to 5, you'll have that, you'll be at 0. And so I know that that means this guy got moved over to 5. If I had some function, say h of x, and it was something like this. If I said, how about x plus 2 equals 0? I could say what input gives me 0 as an output?
Negative 2.
Negative 2. If I plug in a negative 2, I'll have 2 plus 2 squared is 0. And so I'll be right here. And guess what? This is just a parabola, right? Move over 1 this way and you'll be up at 1, right? Move over to negative 1. Negative 1 plus 2 squared is 1 squared is 1. Yep, it moves up to 1. Guess what happens when we go over 2 units? Going from negative 2 units gives me 0. It's the same thing as just plugging in a 2 here. Why? Well, because you'd be plugging in a 0 right there. 0 squared. 0 plus 2 is 2. Squared is 4, and so on and so forth. Going from wherever the vertex is over 1 brings you up 1. Going from where the vertex is over 2 brings you up to 4. And so on and so forth. And that, I think, at least helps me to believe that subtracting from an input moves it to the right, and adding to an input shifts it to the left. Do you buy that?
Yes.
Is that a yes?
Yes.
Okay, cool. So
Sorry, my Wi-Fi is really bad.
it's cool. It's cool. This is so tricky. This is so very tricky because it's opposite of what I would imagine. I would think, well, if you have an input value that corresponds to the x-axis, and if you add to it, shouldn't it move it towards the positive? No, it's kind of backwards, but this is why it's backwards. If you think about it, right? Like this thing is just eventually going to be some number after you do that calculation. The only way that it could be at a minimum, that it could be at the vertex is when the input is 0. There's only one number that's going to make that turn into 0, and it happens to be +5. Huh. And so, yes, it does shift you over. And then if you really need to conceptualize this, I like to think about running. It says you're taking 5 seconds longer to start running. And so, well, it takes 5 seconds to get to where you once were. And so, yeah, okay, that kind of makes sense. Okay, so that's shifting right and left. We're going to come back to this and put this all in one nice looking picture. So we're going to forget about right and left translations, and we're going to talk about up and down translations. This one actually makes a lot more sense. This one is not counterintuitive. In fact, this is very intuitive here. So, excuse me. So, all right, give myself a little bit of room here. So here's my input values, X. My output values, Y. You're stuck, buddy. Get out. It's been climbing between the chairs and stuck. It's cute. Okay, so same function that we began with which we began. Sorry, excuse me. So same function. It's, hey, buddy. Its vertex is at 0, 0. That's right. Yeah, we can't see her today, buddy. I'm sorry. And so it looks like this. We know why. We're not going to go through and play with a bunch of points. We know what this guy looks like. You plug in a 2, you get out a 4. Okay. Now, we started by subtracting from the input, right? Now let's subtract from the output. So what we want to do is talk about, okay, we're gonna have a new function where we take the output of the old thing and then we subtract off 1. Okay, so in other words, f of x was just x squared. Okay, so I'm just replacing that symbol with that symbol. That's all I'm doing. I'm saying, oh, those are the same symbol. I'm just going to replace symbols. And so we have this right here. Okay, and I did this in blue. I wanted to do it in red. G of x equals f of x minus 1, which I said, oh, f of x, that's an output. The output of f of x is x squared. So you take whatever that is, then you subtract off 1. Okay, so that's what I was saying. Now, let's do some points. Plug in a 0. What do we get as an output?
Whoa. 0 minus 1.
So what's 0 minus 1?
Minus 1.
Minus 1. So when my input value is 0, my output value is minus 1. So in other words, we took the vertex and we shifted it down by 1 unit. I'm willing to bet that the overall shape didn't change. I'm willing to bet that all we did, we just took each one of these points and dropped it down by 1. And so this shape should look similar like this. It's just that it's been shifted down by 1 unit. Let's just check that, because it used to be the case that when I plugged in a 1 into x squared, I got out a what?
1.
1. When I plugged in a 2, I got out a what?
4.
Got out a 4. When I plugged in a -1, I got out a what? I'm assuming you said +1. I mean, I said we weren't going to go through and do points. I probably should have, because of what we're about to do. So the conjecture was, well, I subtracted from the input. I saw what it did to the vertex. I took the old vertex, plugged it in, And this new function, f of x squared minus 1, said, well, you just take whatever it was 0, and then you subtract off 1. So it should just drop down to 1. Similarly, when we plugged in a 1, squared it, this is into our first one, we plugged in a 1 and we squared it, it went up to positive 1. This says to do the same thing, but then subtract 1. So it should be the case that this thing just drops down 1 unit, and it should just give me a 0 right here. It should be going through right there. But that's exactly what we should have if these values just dropped down. If every one of these points on this line, if every one of these points on this curve just dropped down by 1 unit, that's exactly what we would expect. So let's check it. We earlier, just a second ago, we plugged in a 2 into the original function and we got out a what?
Wait, will you say that again? You glitched out. I'm sorry, what?
Okay. We plugged 2 into the original function and we got out a what?
4.
A 4. So if this does work, then when I plug in a 2, it should just be shifted down 1 unit. It should just be a 3. Should be the case that when I plug in a 2, I should get out a 3. Why? Well, because every single point on this curve should just be dropped down by 1 unit. Let's check. What is g of 2?
G of 2.
2
equals 2 squared equals 4, 3.
4 minus 1 is 3. So I plug in a 2, I get out a 3, and indeed, that is 1 unit down from the old input. It looks like it. I'm not sure if you believe this, but I believe this, that subtracting a number, subtracting a positive number, I haven't made a point about this, like clearly when I say subtracting a number, I'm not talking about subtracting a negative, because then I would be talking about plussing a positive, right? So subtracting a positive number from the output of a function just drags it down by however many units that is. If I'd subtracted, say, 5, well, what would I do? I would go through and compute all the values, but then it would say, well, then you just do that and then subtract 5. This thing would just be shifted down by a total of 5. Similarly, if I add to the function, let's do a new function, h of x is equal to, say, f of x plus 1. This says we take the outputs of f, whatever they happen to be, and then you add 1. Well, the outputs of f are just whatever you get when you square x. Or similarly, all I've done is I said, well, this symbol means the output of that. That symbol is equal to that guy right there. So I could replace this symbol with this guy. And now I have a new function, h. What happens to the vertex with this guy? Where does the vertex end up?
Doesn't it end up at -1?
Wait, for h?
Oh, that guy. Sorry. No, it ends up at +1.
+1, exactly. Why? Because, well, it used to be, right? When we just did this, we did f, the vertex ended up at 0, 0. Now all we're doing is saying, okay, you do that, then you add 1. Well, okay, well, here I was here, now add 1. And this actually makes a lot more sense to me. You add 1 and it goes to 1. Hey, that's nice, right? So like, this is actually what we're getting at is Adding and subtracting from the outputs does exactly what you expect them to do on the to the graph. You add 1, it shifts it up 1. Add 5, it shifts it up to 5. Subtract 1, subtracts it down to 1. Subtract 27, it would drag it all the way down to minus 27. The thing you got to keep in mind is the inputs are backwards. Adding positive numbers to the inputs shifts it left towards the minuses. Subtracting positive numbers shifts it right towards the positives. I have a picture I'm going to draw right now that will encompass all of this stuff. So give me a second to draw. I really wish my markers were worth a damn, and they're not. So am I good to erase this stuff right now and draw our overarching picture for today?
Yes.
Okay. Now, remember, we've been talking about parabolas, but there's nothing special about this being a parabola. If you think about it, what we've been saying is you have an input and an output. And when you add to the output, well, clearly it moves up because this is the output and so on and so forth. But this is true for the shape of any function. I'm going to draw a parabola here, but I could draw some squiggly, crazy function that I just make up out of the back of my mind. And everything I'm about to draw will be true. The original picture will just be shifted by the same amount. Now, what we're going to assume this whole time is that I'm using a number, A, and A is a positive number. The reason why is just like I said, I don't want there to be any ambiguity with like, wait a minute, is that a minus minus? So is it actually a plus? Or when you go plus A, what if A is negative? Then it's like minus something. Like, no. We're just talking about A is going to be a positive number. Okay. So if this function, if this is f of x, in our case, we've been working with f of x is just x squared, and so it looks like this. Then shifting to the right is what we get by doing so we're on the input axis. To modify the input axis, we mess with the inputs. But the inputs are backwards. So this is f of, now, there's another thing I didn't say. This, of course, is 0. And this distance right here, we're going to call A. And so if we shift it to the right by A units, you could do that by taking x minus A. Just to be clear, let's remember why this was the case. It used to be that when I plugged in a 0 into f, I got out a 0 as my height, right? Well, it's still true that if f of 0 will still be equal to that, you'll still get the same height. But now all we've done is we've rewritten it as minus A. And so the input value we need has to be A. You did that one earlier. Remember when I said, well, what about x minus 5 squared? What input value do I need to be there at the bottom of the at the vertex? And you said, well, it has to be 5. Because that's the only way you could get 0 as an output. So that's all we're saying here too. In order to get, since the output at 0 was 0, the only way to get that same output from this guy is if you plug in an A right there. Similarly, if we wanted to shift this bad boy down to negative A, we would say, well, the thing I would need to, let me do this. Then the thing that I would need to do is the opposite of that. If I want to plug in a negative A and get a 0, then this would have to be fx plus A right there. So this is just a weird thing to remember, right? If you want to shift right, you subtract from the input. You want to shift left, you add to the input. And then you have the easy one, which is if you want to shift up or down, you add or subtract the output. And this will not be drawn to scale because, well, I made this too big. But A will say, okay, if we need to shift this guy up to A, then I just take whatever that output value is. Oops. Write the whole thing. This is what it would look like. I want to take that entire function, f of x, and shift every single point up by A units. Well, then I just take all the output values, f of x, and then I add on A. We saw that earlier, right? If you're at 1, 1 in the original function, and then you add 1, you will be up by 1. If you take the point 2, 4, and then you add 1 more to 4, you'll be up 1 more unit at 5. Similarly, and finally, if you want to take your function f of x and shift every single point down by A units, down here to minus A, well, then we'd have to take each one of the outputs and then subtract off A. So up and down, you plus and minus from the output, right and left, you subtract and add to the input. That's our beautiful picture that we're going to have in our minds for everything that we're going to be doing. Okay, you got this picture?
Yes.
Peter's like, got it. Okay, what I want to do, we're going to go on Desmos real quick.
I love Desmos.
I know, Desmos is the best. Okay, so here we go. I'm going to share my screen. All right, so you see what's going on here?
Uh-huh.
Okay, so right now, the way I've written f of x is equal to x squared. And hey, lo and behold, this is the picture we've been working with. Plug in a 0, you get out a 0. That's your vertex. Plug in, say, a 2, you get out a positive 4, and so on and so forth. Now, let's say I wanted to shift this bad boy right by 2 units. What I would do is say, well, there's a couple ways we could do this. First thing I'm going to do is just straight up just write it out. I'm going to say, well, actually, let's go y equals, I subtract from the input, so x minus 2 quantity squared. Oh, should shift everybody over to the right by 2 units. One way, and again, I'm just going to say this. It used to be the case that when we plug in a 0, we got out a 0. Yeah, plug in f of 0 equals 0, and that's why that works. Now, in order to get out a 0, I have to move over to 2, because when I plug in a 2, 2 minus 2 is 0, and now that's why that guy got shifted over 2 units to the right. And doing that took every single input value with him. not just that one point, right? It's like, it's still the case now, but if you kept going, like you're at 2, so you go 2 minus 2 is 0. Now move over one more, move over to 3. Then what happens? Well, 3 minus 2 is 1. Oh, it's just kind of like when I was at my original function here at 0, moved over to 1 and I got 1. Now, if I'm at my new vertex and I move over 1, well, I should get 1 again. If I'm at my new vertex and move over 2, which is now 4, I go up to 4. Because 4 minus 2 is 2 squared is 4, so on and so forth. Now, that's one way of doing this. I could have just told Desmos, hey, just compute f of x minus 2. Oh, and look at that. You can see, you're like, nothing happened. Well, yeah, you see, it's doing it in black. If I turn it off, we can see, yeah, it directly goes over the old one. That's because they are exactly the same thing. F of x minus 2 is the same thing as x minus 2 squared, which I'm graphing both of them. But this is what I really like about Desmos. So in fact, I'm going to go ahead and I'll get rid of both of these because I don't want to use black. I'm going to do this. So let's graph f of x. How about minus h? Now, you see when I do that, now I've added in a parameter. Desmos is expecting either x's or y's because it knows that my input value is x, my output value is y. And so now I've added in an h. And it's going to say, what's h? I don't know what h is. Would you like to decide what h is? And it's asking us to add a slider. And so what I'm going to do is say, yeah, let's add that slider. And right now, you could see that slider there. It goes from -10 all the way up to 10, and we're going to play with it in just a second. But what this is the what it's doing right now. Why did it do it in red? I was expecting a different color. Can I change this color? Nah, it's not letting me. Whatever. Okay, doesn't matter. So right now it's saying that h is 1. Well, so in other words, that's f of x minus 1. We should expect that this new function should be shifted 1 unit to the right, and it looks like it is. Now watch what happens when I grab this slider. This is cool. Okay, if I move the slider to the right, h is going to get larger. And now when h is 2, the vertex has been shifted over 2 units. Well, in fact, every point on this guy has been shifted over 2 units. But in particular, I'm going to watch the vertex as we go and do all this stuff we're about to do. So, okay, if I slide this over to 6, that vertex should end up at 6 because that would be f of x minus 6. Let's see what happens. And yep, there you go. The graph on the right is plotting f of x minus 6. That shifts the entire graph to the right by 6 units. I could shift it over to the left as well by making these positive values or making them negative values. So now we have f of x minus -4. That's the same thing as f of x plus 4, which of course shifted everything to the left because now it's the case. What number do I need to plug in to get me back down to 0? Well, the input to the original has to be 0. And so to get a 0 as an input, that would need to be a -4 because -4 minus -4 is -4 plus 4, which is 0. And that's why it does that. Now, let's look at f of x plus k. And we are going to add the slider k. There we go. There's my k. And we can see, okay, when k equals 1, in fact, I'm going to get rid of f of x minus h right now. We're going to hide him. And we're just going to look at f of x plus k. What this thing is doing is taking all of the output values, and then it's adding 1 to them. And so when we were at 0, 0, Now that output value gets 1 added to it, and we are now shifted up to 1. Now I'm going to slide this up one more. So now we're at f of x plus k is f of x plus 2. And we could see that the vertex ended up at the point 0, 2. And again, all of the original values of f have been shifted up by a value of 2. If we go down to -2, what this is plotting is f of x minus 2. And so it takes all of the output values of the red function and just drops every single point down 2 units. There we go. Now, let's do one more thing. F of x minus h plus k. Now we have 2 things to play with. F of x minus h. Let's start somewhere nice. Let's start at 1, 1. 1, 1. Okay. I'm going to get rid of the green one right now because that's ugly. In fact, let's start at 2, 2. That's easier to see with this, the way this is graded. Okay. So the black function is f of x minus h plus k. So what we've done is we have shifted to the right by h units. H in this case is 2. And then we have shifted up by 2 units because k is 2. That's what this thing is plotting. Just to be really, really clear. This is all symbolic and crazy stuff like that. I want to be absolutely clear of what I'm plotting there in black. It's f of x minus h, which is, well, x minus f of x minus h would be x minus h quantity squared. Why aren't you giving me any new colors? This is really bugging me here. There. Thank you. All right. Now, f of x minus h squared plus k. And you could see that, yes, the black and the green functions are exactly the same thing, right? Here's the black one. And when I turn on the green one, yep, it overlays directly above it. There's no difference. Just one way is a fancy way of writing the other. In fact, one way, the one with the F, is nice because it generalizes really easily. But now what we could do is say, okay, well, then if I know where this vertex is, or like if I'm given a function with a certain vertex, like if I know the vertex is at -4, I could easily find a formula for this guy. Similarly, and this is where it all comes back together. It's like, does this form look familiar? This f of, or this x minus h squared plus k looks very, very familiar. And so if we are given some kind of quadratic polynomial, we can change it around. Okay, but he really wants a sandwich. We're going to get him a sandwich real soon. So what we can do is write it in this form and say, oh, hey, look at that. Like if I ended up with, let's say, x plus 3 squared, or yeah, x plus 3 quantity squared minus 2. I'd say, okay, well, the x plus 3, well, I'd have to go to -3 because that's the funky part. But I know, like, I'm not doing this with actual sliders. I'm just thinking, well, x plus 3 means that you took your vertex and you moved it to the left. You see, I even screwed that up. Plus 3 means you're moving it to the left by 3 units. And then -4 means you've dragged it down 4 units. And so I could see, like, Well, then this green thing is what it would look like. If we had if we had the polynomial x minus 2, so okay, that means that we've shifted the thing over to 2. Or actually, let's do it this way. This just to be really, really clear here, because what we're actually imagining is that we're starting here at 0, 0, that you're just taking your bare bones x squared polynomial and you're saying, okay, x minus 2 squared. Oh, that's a shift to the right by 2 units. So I go to x minus 2. And so I can imagine, okay, that's what that would look like. And then if it were x minus 2 squared, say plus 4, and I'd say, then what I'm doing is I'm adding 4. So I'm shifting this picture up to 4. And now I could actually graph what we're looking for. Only thing that's left to do is deal with, there's one letter missing from our general form, and that's A, right? Because the way we wrote these things was A x minus h squared plus k. And so tomorrow or Friday, we're going to talk about what multiplying an output does to the graph of the function. But for right now, we have enough to be able to at least graph these things. So does this help, like actually seeing this with the sliders and stuff?
Yes, it does.
Cool. Okay. So, okay, one last thing. I know we're like 30 minutes over. So your homework, and like I said before, I was going to wait and see how far along into our talk we got. I think what we're going to do for homework is I'm going to give you something like this. In every case, it's going to be like this, and so it'll be like this. Let's do it that way. Okay. I'm going to give you something like this. What I'm going to tell you to do is rewrite this in the form A, although it's not going to be any A's because we have not discussed how to do A's. We're going to say rewrite this in the form like that. In other words, complete the square. And so you're going to take this and complete the square by doing this. You're going to say, okay, x squared plus 4x is 8. And you're going to say, okay, I take half of the middle thing, I add it and subtract it like that. That gives me the perfect square right there, which is x plus 2 quantity squared minus 2 squared. That's 8. Equals x plus 2 squared minus 4 minus 8. Yeah, minus 4 minus 8. Yeah. And so you're going to say, okay, x plus 2 squared minus 12. Okay, so this is what you're going to do. That's part 1. Well, I'm not, don't think about parts. This is just, I will be very explicit about what I want you to do, but this is going to be the general idea. I'm going to give you something like this. I'm going to tell you to graph it we're going to do something like this. I'm going to tell you to do this first. Put it into this form. Then what I'm going to want is words. And I'm going to say, like, how is this related to the function x squared? And who cares about the g of x? But what I'm going to say is, like, how is this related to x squared? And what I'm looking for is, this is the graph of x squared. Shifted, so look at this guy right here. Shifted how much in what direction?
Left.
Shifted left. So here we go. Shifted left. How many units?
2 units.
2 units. And shifted which way? How many units?
Down 12 units.
12 units. Okay. And I'm pretty sure, like, after having written that, you should be able to draw it. But here's the problem. Whenever we draw something, so let's just naively move along and say, okay, let's say I want to draw this guy. And so I go left 2 units, down 12 units, and I go like this. Okay, well, here's 2 minus 2. Here's 12 minus 12. Here's the problem. Uh-oh. Does it go like this? Does it go like this? Does it go actually through the origin? Or does it miss it altogether? Is it really, really thin like this to where it doesn't go through at all? Uh-oh. Well, this goes back to like week 1 stuff or maybe week 2 stuff where it's like, well, wait a second, axes, right? If I want to know where something goes through an x-axis, if I'm on the x-axis, what is my y value? If I'm right here, Kayla, what value of y is it?
0.
0. If I'm right here, what value of y do I have?
0.
Always. So if you're on the x-axis, your y value is 0. This is your y value. So in other words, to find x-intercepts, set y, which is your f of x, equal to 0 and solve for x. So in this case, we would say, okay, this thing equal to 0 equals x plus 2 squared minus 12. I'll bring the 12 over to this side, equals x plus 2 quantity squared. We take a square root of both sides. I get a plus and minus. I get plus minus 12, which you can reduce if you want. I don't care. Subtract the 2 and I get minus 2 plus or minus root 12 equals x. I happen to know that root 12 is bigger than negative 2. How do I know that? Well, 4 is less than 12. Take the square root of both sides and I get 2 is less than root 12. And so, and if this is, if just thinking about it doesn't come to you, just use a calculator and see which one, see if these are both positive, both negative, positive and negative, whatever. But I know that root 12 is bigger than 2. And so when I take minus 2 plus root 12, that's going to be a positive number. I know that minus 2 minus root 12 is going to be a negative number. So the picture is starting to become clearer. And I can say, okay, all right. We're shifted 2 units left, 12 units down. So my vertex is right here. I'm at minus, which must be over here. Minus 2 minus root 12. I've labeled that point. The other one is minus 2 plus root 12, which I know is a positive number. Minus 2 plus root 12. And so it has to look something like this. Sorry, that looks terrible. It has to look something like this. The only thing that's left is, oh, where does it go through the y-axis? If you're on the y-axis, what is the x value? Oh, I'm erasing this. Can I erase stuff?
Well, hold on, sorry.
Okay.
Okay, yeah, we're good.
Okay, so so we just said to find x-intercepts, you set y equal to 0 and solve for x.
Mhm.
To find a y-intercept, if I'm on the y-axis, what is my x value?
0.
Yeah. Set x equal to 0. And so, in other words, we're computing what the output value is when I plug in a 0. Well, this says 0 plus 2 squared minus 12. 0 plus 2 squared is 4 minus 12. 4 minus 12 is minus 8. And so, and this jives with my picture. It should be a negative number right there. And so we get as an output minus 8 right there. The really tricky thing is getting these guys right. But I am so okay with you using a calculator, like if you want to see, but you are definitely going to want to see when you get stuff like this and you solve, you're going to get -2 plus or minus the square root of something. It's not always easy to see if they're both positive, both negative, or where they show up. But finding out whether they're both positive, both negative, or one positive, one negative will help you draw this picture. As you can see, it doesn't need to look good, but it does need to be, as I've said 100 times, qualitatively accurate. I'm going to be looking for a vertex. I'm going to be looking for all the intercepts on both the x and the y axis. And I will want this in words, right?